Welcome to this explainer. Today, we are taking a really fascinating journey that bridges two seemingly totally different worlds. We're going to bridge the gap between qualitative research design and the cutting-edge realm of quantitative financial machine learning. Whether you're building a foundational theoretical framework or stress testing massive financial data sets, the core principles of rigorous inquiry, they're exactly the same. Let's get into it.
Okay, let's dive into this. Here is our structured roadmap for today. First, frameworks of scientific inquiry. Second, method versus methodology. Third, the 4 research phases. Then, financial backtesting and metrics. And finally, validating data with machine learning. We are literally journeying from abstract social science right to the forefront of high-tech data validation.
So let's kick things off with Section 1, Frameworks of Scientific Inquiry.
All robust research, and I mean whether it's a high school student's first portfolio project or a seasoned scholar's PhD dissertation, it all begins with a solid blueprint. Without it, you're basically building a house with no foundation. And that foundation is your conceptual framework. It's essentially this visual representation of expected causal relationships. Long before a single piece of data is collected, researchers map out exactly how they view the problem. They pull from existing theoretical literature to draw connections between variables. It's exactly how you develop your research questions and hypotheses, giving you a crystal-clear lens to view your target problem through. Now, setting up that framework involves meticulous documentation. The steps for original research require you to formulate a research question, select a methodology, and document your process and data sources way before producing the actual written paper. And honestly, this isn't just busy work. Whether you're a high schooler starting a research journal or a postdoc mapping out complex variables, documenting these early decisions showcases crucial intellectual development. It proves your process, not just your final output.
Moving right along to Section 2, Method versus Methodology.
Okay, stepping into the philosophical core of research, we really need to clarify 2 terms that confuse even seasoned academics. Let's start with methodology. This is the overarching strategy and philosophy behind your research design. It explains your worldview and the core reasoning for your approach. It's that higher-level thinking that guides you. Methodology essentially answers the critical how and why behind what you're doing. Like, why take a qualitative approach versus a quantitative one? That's your methodology at work.
And this brilliantly illustrates the concept. Imagine you're building a piece of flat-pack, self-assembly furniture. The methodology is your overarching approach to the entire project. Are you the kind of person who reads the manual from start to finish? A structured step-by-step planner? Or do you just kind of freestyle it, taking an exploratory approach and figuring it out as you go? Your methodology reflects your perspective, your starting point, and the very principles shaping your decisions.
So, to compare them directly, methodology is your game plan, your big-picture strategy. The method, on the other hand, refers to the specific tools you use. Sticking with our flat-pack furniture analogy here, if methodology is your approach to reading the instructions, the methods are the screwdrivers, the Allen keys, and those tiny little wooden dowels you use to put the whole shebang together. Methods are the on-the-ground practical techniques, like surveys or interviews, that you actually use to gather your data. Let's move to Section 3, the 4 research phases.
So let's see how this builds. How do scholars actually structure their work once the strategy and tools are locked in? Well, it builds across 4 distinct phases. Phase 1 is conceptual, demarcating the study focus and formulating the problem based on gaps in knowledge. Phase 2 is designing and planning, laying the foundation, picking your methods, considering ethics and timelines. Phase 3 is the empirical phase, the actual operationalization where you're out there collecting data that aligns with your theoretical framework. And finally, Phase 4 is the analytical phase. This is where you process and interpret all that collected data using statistical or qualitative techniques to finally test your hypotheses.
Which brings us to Section 4, Financial Backtesting and Metrics. Let's take this analytical phase and apply it to a highly complex quantitative environment, financial markets. In finance, the ultimate analytical phase is backtesting a trading strategy. You do this using key metrics like the Sharpe ratio, maximum drop, profit factor, number of trades, volatility, and the calm rate. So the crucial point is that backtesting evaluates historical trading performance. Think of it like a doctor diagnosing a patient based strictly on their medical history. By applying a strategy to historical data for stocks, say Apple or Amazon, and analyzing these backward performance metrics, financial researchers can estimate future profitability and really assess the risk.
But what happens when we look at this from a macro level? Consider this number, 3,000.
That is the number of daily incoming financial market time series managed by modern central banks. That is absolutely massive. We're talking equity, interest rates, foreign exchange, commodities, spread across 70 geographical markets every single day.
So ask yourself, what happens when we scale data validation up to 3,000 daily market series? You have your historical metrics, you've got your methodology, sure, but manual validation at this kind of scale, it's literally impossible. You can't just have a human manually checking 3,000 series for errors, anomalies, or data corruption. There's just no way. We need an automated solution.
And that brings us to our final section, Section 5, Validating Data with Machine Learning.
Now, what's really interesting about this is that traditional validation methods, like simple graphical checks or basic threshold warnings, they just aren't enough anymore. They yield way too many false positives and false negatives. We have to take a modern data science approach. Take a look at this specific anomaly in the Shanghai Stock Exchange A-share index. Notice that tiny, almost imperceptible drop right there? Traditional threshold warnings might completely miss this. Why? Because the data point, while highly suspicious, might technically fall within a basic, pre-programmed accepted range. To a human eye scanning thousands of graphs, it's basically invisible.
Let's look at a second example, this time from the U.S. money markets, specifically the Secured Overnight Financing Rate, or SOFR. Notice the flat line happening here. Financial market series undergo structural changes all the time. When market dynamics evolve, it becomes incredibly difficult to fit a traditional, static model to the data. You absolutely need a system that understands the unique, shifting context of each specific instrument. When we compare these anomalies side by side, we see a huge problem. These are false negative errors. The system thinks the data is totally fine when actually there's a serious anomaly. Now, you might argue, hey, an occasional false alarm keeps a statistician on their toes. And sure, maybe. But in the long term, chronic false alarms or missed anomalies cause human experts to just become accustomed to the noise. They start flat out ignoring warning messages, which leads to massive operational risks. We desperately need a better system that cuts through the noise. Enter machine learning, specifically recurrent neural networks like long short-term memory, or LSTM models. What makes LSTMs such a game-changer for this methodology is their ability to capture long-term contexts in sequential time series data, and they do this without suffering from what data scientists call vanishing gradients. The model dynamically adapts to evolving market environments. It acts just like a subject matter expert, filtering out useful explanatory features from thousands of series to accurately predict what a data point should be, then it flags it if it deviates from that highly educated prediction. Here, we can walk through this stylized end-to-end blueprint of the automated data validation process. You see the workflow moving from input data to filtering features, right into the ML prediction model, and finally landing on the error assessment. By leveraging the fact that financial series are often highly correlated, like, for example, instruments with similar maturities often move together, this ML workflow severely limits human intervention. It scales validation efficiently, running continuously every single day to detect true anomalies without absolutely overwhelming statisticians with false alarms.
Wow, we've covered some incredible ground today. We moved from the philosophical distinctions of research methodology all the way to deploying long short-term models to validate central bank data. But the foundational importance of a clear framework remains constant, no matter the scale. So I want to leave you with this final, provocative thought. How can you apply these robust validation frameworks and methodologies to stress test your own data projects? Think about your blueprint. Thanks for joining me, and I'll see you in the next explainer.